Hello, good afternoon. Raúl here, already fourth year PhD student under supervision of Manuel Soler and Rono Cavallaro. And now it's time to talk about hydrogen aviation. So as previously motivated, aviation is a contributor to climate change. And between these main agents, these main drivers of impact, we can divide them into two groups, carbon dioxide and non-carbon dioxide emissions or effects that contribute 1/3 and 2/3 of this aggregated number, respectively. So with that and an increasing traffic and traffic demand, there is the urgent need to have quick and disruptive measures that also, as explained before, we can divide into three blocks. First one, operational, more focused on non-CO2 emissions. Secondly, technological, changing forms of propulsion, forms of fuels, and also advancements in drag and consumption rates. And above both them, policy-based, basically rewarding or penalizing good and bad practices. So among all of these, hydrogen has emerged as a long-term sustainable solution for aviation, where we directly eliminate CO2 emissions, and it can be also produced by renewable sources. On the other hand, what happens with non-CO2? We have problems here because we have an increase in water vapor and also a potential increase in contrails that can play an equally or even larger noxious role to the environment. And also, we still have a big kind of unknown or basically uncertainty about the NOx emissions that can produce a hydrogen engine. Good part is that the mitigation of these effects has been proved promising through operational strategies, such as presented before. They have a strong dependency on tough location, so we can reroute the aircraft in order to avoid it. So basically, this thesis was born with the idea of joining the research and design of the hydrogen aircraft with the operational trajectory study to round off the problem and tackling both CO2 and non-CO2 effects. So this would be kind of the scheme of this thesis, joining hydrogen aircraft design optimization with the optimal trajectory planning, with the general objective to analyze the introduction of this hydrogen aircraft, quantifying its climate impact reduction potential and derived cost, with the sub-objectives of deriving or developing aircraft design analysis and optimization models, and also climate optimal trajectory planning algorithms for the hydrogen aircraft, with the relevant research questions that I will develop later in each of the blocks. So, starting from the design, the MDO, the multidisciplinary design optimization, it is clear that we need digital tools to predict the potential of this new technology, and here is where design analysis and optimization have a role that comes to play. It's basically transforming the design problem into an optimization problem with objective function to minimize, varying the design variables that are characteristics related to the plane, and with some constraints like fulfilling a mission. If we go through the state of art of hydrogen aircraft multidisciplinary design optimization, we found a bunch of works, each of them from different perspectives, that they lack a holistic view or a comprehensive work of all the aircraft itself with all the subsystems and with also quantifying its impact or emissions. So we found the need to understand the impact of the mission objective on the design, basically the main drivers of design, and also to be able to measure the capabilities of this aircraft under different conditions. So basically trying to answer the questions of what are these conceptual design hydrogen aircraft models, which is its feasibility and maximum capabilities, which are their design and performance drivers, and what are their most beneficial configurations. We're trying to answer all of this in all the work that I've been doing last year, also already presented in these doctoral meetings that we wrap up in this paper, already sent to the Journal of Aircraft, where we compare this conceptual hydrogen design against a conventional kerosene reference, measuring its feasibility capabilities, also these main design performance drivers, and with a quantification of impact and cost. I'm going to skip these results for today. So with these results, we jump now into the trajectory optimization part, and for that, we need to transform these aircraft models, these aircraft candidates, into dynamical models. So basically, into smooth, cheap, and differentiable functions that can be embedded in a trajectory optimization problem, in this case, in a point mass dynamics. in a trajectory optimization problem that can be formulated as this, again, with objective function, with this point mass dynamics, and with the path extents constraints. So if we go now again into the climate So at the time of solving this problem, we have different methodologies that can be through optimal control solutions, direct and indirect methods, and also with non-optimal control ones that could be metaheuristic, gradient-based, nonlinear programming, or mathematical programming. So if we go now, yes, again, into the state of art of climate optimal trajectory optimization, as Omar represented before, we also lack work here related to hydrogen aircraft that has been not done yet. So to cover this gap, we propose here 2 studies. First one to solve through the indirect solution via the point-triggering maximum principle. This is more focused into a theoretical approach to solve canonical problems and to be able to understand the optimal operating conditions of this aircraft. And focus, basically this part is focused more on the influence on performance, more qualitative than quantitative. And a second study directly using ROC in-house library for free routing trajectory optimization into a more realistic study where we also include the climate impact. These 2 studies comes with the purpose of answering the research questions that which are the optimal operational flying conditions and which are the optimal climate routes for this hydrogen aircraft. So for the first study, we do a full cost optimal cruise for a transport aircraft. This is a 1D cruise flight with constant altitude where we assume a quasi-steady flight, meaning that we don't have acceleration. And we can formulate the problem as this one, again with the reduced dynamics and with the velocity as the control. We use here the point-triggering maximum principle to reduce the problem to a 2-point boundary value problem, to which we add altitude as a state design variable. So we want to know the optimal altitude to perform this cruise, and we also add the mass consistency. So we end up with these 3 constraints and 4 design variable optimization problem that we are going to solve. This will be the solution for the full optimal cruise, just caring about the consumption, not the time. And this will be at 4 different ranges, the solution for the hydrogen aircraft at 5 different payloads. So solving the PMP and the mass constraint consistency and the different the solutions in terms of consumed hydrogen or consumed fuel. As you can see in the stars, this would be the optimal altitude of each of these conditions that we can basically also see the trajectory profile, how it looks like, how it evolves, the optimal altitude as we increase the payload, and also the velocity and thrust and mass evolution. What we are really interested here is to compare this against the kerosene or the conventional aircraft to see how this optimal solution evolved. So to give you some highlights of these results, we can compare the optimal altitude. In this case, we achieve nearly between 300 and 600 meters of difference in this optimal altitude. That is 1 flight level that could be a potential help, could be of potential help in the future when segregating traffic. We also have here the difference in the initial mass. As you can see, the increase in for hydrogen, it's up to more than 8 tons. That is reduced, increasing the range due to its bigger efficiency, higher efficiency, sorry. And in terms of emission and cost, we can see the reduction of the in carbon dioxide depending on the manufacturing method of the hydrogen. Obviously the increasing water vapor and increasing cost, assuming the cost of producing or getting both of the fuels. For the second study, in this case, we use in-house ROC library for free routing trajectory optimization, joined with COSIP grid model for estimating the energy forcing of the potential contrails. In this study case of a 4D trajectory between Tenerife and London, in this objective function with 3 objectives: fuel, time, and climate impact in terms of contrail energy forcing. So this would be the solutions. We have here 4 different trajectories: blue for hydrogen, yellow for kerosene. The dotted lines are for the cost optimal trajectories, just caring about fuel and time. And in the constant lines, we also include the energy forcing of the contrails. As you can see in the figures, this top row would be the energy forcing of the created contrails by kerosene at 4 different altitudes, and this one for the hydrogen. In these bumpy climate optimal trajectories, both aircraft are trying to follow the blue spots where the cool contrails are formed, and they are trying to avoid the warming ones to reduce this accumulated energy forcing. With that, I'm finished. As future work, it would be to wrap up all this hydrogen aircraft trajectory optimization work into one paper and to basically write my thesis. As future research lines, we need more research and development on basically non-CO2 emissions related to the hydrogen aircraft, and also it would be great to have high fidelity or validated models for the hydrogen subsystems as the engine and the cryogenic tank. This is a summary of the achievements, my research stay, the journal papers, and the conference papers, and basically that's all for today. Thank you very much.